Hello folks, we're going to do some programming in differential data flow today, or we're going to try at least. What I thought we'd do is head on over to Advent of Code, which is an interesting sort of website where they, in the days leading up to Christmas time, give you various little programming tasks that start, if I remember correctly, start relatively easy and build up. And I thought we'd go through a few of those as time permits. They each have the structure, so there's 25 of them, and they drop in the days leading up through the holidays. Each one has a little description. There's some narrative, whatever, that you can read and try to. This is something about submarines, if I remember correctly. And ultimately, though, what it gets to is a little task. Task that you have to get your head around. You have to frame it appropriately, I suppose, model it in your program, and then answer some questions. And they basically hand you a big pile of data. So let's take a look. Here's a big pile of data that we might get handed. You can see lots and lots of numbers and stuff there, and some answer that you have to put in. And for each of these, once you've done, for each day, once you've done sort of the problem, you get a second half. You don't get the second half until you get the answer to the first half. And I don't know, they're usually related, though sometimes you have to fundamentally restructure how you're doing things. So let's take a little stab at some of these. What I've done, just for my own personal use, is put together. I did this back in 2017, so this is the differential data flow repo, actually. And there is a directory there, Advent of Code 2017, and you can dive in there, and there's a whole bunch of, I guess I did 17-ish of the days. Looks like I skipped 16 and then just stopped. The complexity gets to a level, in my experience at least, where you can continue to write these things, but it's not as satisfying as you might hope. It was just sort of pushing through. So I thought I'd do something similar over here in Advent of Code 2021, a brand new directory where I've just added in timely and differential data flow dependencies, and we'll start populating some little differential data flow programs. Here's an example, which just make like a little bit bigger for everyone to be able to see this. I have no idea what this was doing, but one of the things you have to do is figure out how to capture all the input. And load it on up, and to be totally honest, like often a lot of this is not thinking about how to do computation so much as thinking about how to parse strings and break crud like that apart. But let's give this a go. So we need to do a few things. We need to go over here. We need to cd source and make dir bin, and hop back down there, and we can grab an example, like if we just okay, that was a mistake. Apparently the shell does not like what I was getting at it. But let's wander over here and plop that in there. This is not the same problem, but I just want to make sure that we can run things and see what happens. And probably there's some, well, maybe there's some arguments that need to come in from the input. We shall see. All right, looks like this is probably. Well, in the intervening 4 years, probably some code that has changed. We'll try to figure this out once we get a take on the problem that we're trying to solve. So let's look. Day one, great. We are at C. This is. Sort of telling you that in the 25 days leading up to Christmas, you want to collect all of these. You get a star for each each puzzle that you solved, 2 for each day because they're 2 parts. So the first problem, we're going to have the following sort of setup. Someone's going to show us a whole bunch of seafloor depths, looks like, increasing as they go out. Or sorry, not necessarily increasing. Increasing in distance from the submarine, but the heights, they're going up and down. You can sort of see, let those go up. And what we want to count, looks like, here is the number of times a depth measurement increases. I should say, sorry, these go down. This is depth. So this is not altitude above the seafloor or something. This is distance below sea level, I presume. So we need to put together something that can consume somehow a sequence of numbers and report on adjacent numbers, essentially, to say, like, for these two, did it increase, decrease, what happened? And we'll need to take this massive pile of stuff here and determine, basically get that count for each of these things. So let's return to our program here. Let's see if we can figure out, I might just delete a bunch of things, but we will need to figure out why this input trait is not being used, and this, why we're having such a hard time creating a new input at the same time. Mysterious, right? So let us see. Well, so this is day 1 again. So let's bump that up there. Hopefully that link still works. Well, we'll find out. We are going to have a different form of input. We're just giving this massive long list of things. We might be able to structure that. Let's see. As a vec where we have jammed in. Let's see what this looks like when we copy and paste it into here. Yeah, well, that's pretty horrible, isn't it? Let's see if we can. What do I want to do? I kind of want to indent all these a bunch and put commas between them. What a beastly. So if we do that a bunch, hopefully we have no other. So we've got a lot of commas in there now. And as a consequence, I can now collapse it down. Great. So that's our input. We'll return to that in a bit, but hopefully never have to expand it back out again. And maybe we'll need length later on, but I think could also do input.len. So let's try to figure out what's going on here. We have sorry, this is all prep work basically. This is trying to think through how might we want to distribute the work across multiple workers. Let's just simplify that for the moment. Not try to do that up there, though we could try to make things a little prettier in the future if we want. So this new collection from nonsense is, I think, where the pain and stress and whatnot was. So let's just see if we can get this data in as a collection, I suppose, of data. And we'll see, actually, I think up above, what we might want to use some of the Rust iterator stuff for. In particular, we're going to want to associate like a position with each of those elements. First record should be position 0, then position 1, that sort of thing. But let's just imagine we still call it input, and we're going to try to create a new depths, let's call it. And we're going to have input. Maybe we'll just do the dot map of depth. Input dot. We can just do, I think, right, input dot into iter dot enumerate. And that will produce pairs of the position, 0, 1, 2, 3, 4, and the depth readings. And now we'll want to do a toStream into the scope. This will create a timely data flow stream on each worker, so we want to be a little careful actually, but timely data flow stream on each worker that is not yet differential data flow, but it's going to have our data in it at least, and we can start to manipulate it. Great. I'm just going to call this for simplicity, for clarity, all depths. And I'm just going to delete all this stuff. We'll reproduce it. Let's see if this is no method toStream. That's absolutely right. So we're going to want to use a few additional. Use the toStream operator. This great isn't what we want. Sorry. Timely data flow operators. Cannot move out of input. That's a great point. So we'll want to. Well, we can do a few different things. This is probably the easiest. Great. So we've gotten our data into timely data flow in the sense that this massive pile of data up here is now available as a stream contributed. Okay, this is going to be awkward. Contributed by each of the workers, which means we'll have as many copies of this data as we have workers that are out there. It's still just a timely data flow stream though, so we don't actually have any differential data flow methods available on it yet. We need to do a little bit of moving stuff around. So let's do a little bit of this actually. Before we do that, let's narrow down our depths to the workers depths. So something like all depths dot filter, and we've got a index and depth as well. Basically, the two things are recorded because we enumerated everything. And we're going to keep those things where index mod peers. Okay, we have two things called index, unfortunately now. IDX. So this will restrict our attention, restrict the contributions of each of the workers to just, just those that. It's going to take all of the positions and depth measurements and ensure that each one emerges only once through one worker. It's going to happen to be the worker identified by taking the index and using the mod of the number of workers we have going. And this is just to stay sane, so that we don't introduce 5 copies of the depth method measurements if we have 5 workers up and running. All right, so we're going to need to use some more operators here. I think we probably just throw it up here. We're probably going to have a few more, to be totally honest. Peers does not live long enough. All right, so this is a classic. Sorry, I'm remembering various trustisms as we go. Both index and peers are going to be captured by this closure, or may be captured by this closure. And if we don't use the move keyword, we'll try to capture them by reference. However, they don't live long enough because this data flow call will return. And at this point in the code here, well, actually, they're still alive there. Anyhow, it gets stressed out about their lifetime. So let's see. I'm gonna Rust unhelpfully is telling us about a bunch of differential data flow warnings, which I'm just going to comment out for the moment. And like absolutely unrelated things. So here we are back in differential data flow land. We don't need this input thingy yet. We will eventually want these operators, so I'm going to not get too stressed about that. Rust would love us to clue it in when we're not going to use variable, and that suppresses the volume of warnings that we have to look at. But we haven't used our depths yet. Let's just count them up. Actually, sorry, count them up. We can't count them up yet. We have to take our collection of data and turn it into a differential data flow collection. Now, what does that mean? For each of these index, comma, depth measurements we have, differential data flow wants us to present it as some data, which is going to be that pair of values, comma, a time. We'll see what that means. Comma, a diff, like a +1, -1, some sort of change that's going on. So let's take, we're going to take all depths here. We'll do this this filter, but we're also going to do a map right after, which is going to move IDX depth into a new IDK, yeah, great, into a new record, which is IDX depth, the same data as we had before, but now a time. In this data flow, and I don't know if this is going to be important, we're using the empty tuple as our time type, which is to say there's only one moment in the computation, things happen, and that's it, which isn't much of a data changes, streaming, what have you, but that's fine. I mean, it's fine in the sense that like nothing's wrong with that. We're still going to be able to go and get our answers. Nothing about the problem asks us really to do a lot of streaming. And now we're going to turn this into a collection. And we'll see if we can find as collection. We'll need to add a map up here as well. As collection, all right. So method not found, which is almost certainly because we need to go and use it. And I need to remember where. Great, so it's just something defined on, oh, sorry, it's in collection. See if that works. Okay. Did I mistype a thing? Oh no, sorry, that's unused import. Sorry. Method not found in stream. Blah 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 blah. Blah integer. Well, okay. A little drink here. We will need to figure out why this is. Classic tedious combination of Rust and the way differential data flow has been written, where the resolution of these sorts of things. So we have as collection here. It has a method as collection. It turns things into a collection. And what's unclear is why this is not panning out. So we'll ponder it for a little while. What are we learning? This is the timestamp type, as far as I'm aware. If we look over here, sorry, if we sort of look at this error, the type looks right. It's data type, pair of VU size and integer. Haven't figured out what the integer is yet. The empty time type, and then an integer. So let's just bind this for a moment. This is now still a timely data flow stream. We'll let this is all that as collection is doing. Let's see if we get a more appealing error. Expected. Oh yeah, expected a stream, found a stream. Okay, so this is Rust. This is not our fault. well, it's our fault, I suppose, but it finally gives us the error we were looking for, which is we're using two different versions of the timely data flow create. So if we look over the setup here, we have differential data flow, which is not pointing at the same repository as timely data flow. Let's see if this. This is me trying to remember what the various paths are to things. Just make sure our project's timely / timely data flow / timely. Still some mismatched types. I suppose we should look at differential data flows timely reference and see what it uses. Oh, is there not a? Oh, this is in the text. Well, let's see. Where's the root timely? Oh, what a nuisance. This is apparently the current version of timely that is used in whatever I've got going on at the moment. So now that these, well, now that they match, hopefully this great. All right. Or so hold on. So we've now got all of this nonsense. We should just be able to type as collection here and skip this stuff and remove a warning. And great. Okay. Now, now let's do a few things. For example, we can do, just to check things out, our depths dot map, and we're just gonna map everything to the empty tuple so that we can count it and then inspect the results. So this will take every record we have written down in there, say, I really don't care about your data at all, I just want you to do the empty tuple. Count then takes a collection of whatever records you have, and for every record that's potentially present in it, for every record that is present in it, it tells you the count, the number of occurrences associated with it. Which, if we've told everyone to become the empty tuple, should just be the number of records we have in it. And then inspect tells us, well, inspect allows us to run and arbitrate a little bit of code on whatever records are there. So this is telling us, if we look over here, that at time the empty tuple, there is one occurrence of the pair empty tuple comma 2000, since we turned everything into an empty tuple, and we could have made this be the number 5 instead, or something like that. But there are 2000 lines, if you will. Great. So what do we want to do now? We don't actually want to print out the count there. What we'd like to do is figure out how many times the depth increases, I believe. Let's close this nonsense down. We're going to try to count the number of times. I mean, we need to determine increase versus not increase, but a depth measurement increases, so stayed the same is not correct. So great. Well, how do we do that? How do we look at two adjacent bits of data? We put these indexes on there, and so what we need to do is line up data that have the same sort of it says the same plus or minus 1 index, right? So we might like to take every index, let's do, sorry, let's call this depths now that, the right way, for me at least, the right mental model for programming with differential data flow is that you pretend as if you're writing a single-threaded thing. You make sure to load the data appropriately so that this is correct, but then you start programming as if you're basically just writing a single-thread data. So you've got all of your depths sitting in front of you. We happen to know that they're distributed across multiple workers, but you still, just in terms of your brain, it helps to not, for me, it helps to not think anymore about which workers are where. So we're going to take depths, which have an index and a depth measurement, and we're going to join this again with depths, except that we'll want to find the next reading. So if this is index and depth, then we'll want to map this to, we want to find the next one. So we'd like to subtract 1 from the index and depth. Now, hopefully, so we're going to align each depth measurement with the next measurement. For things that don't have a, let's try to say the index of 0, for example, we can subtract 1 from it, and I don't know what that'll turn out to be, something horrible probably. But we might actually see that it turns into a panic because Rust panics if you wrap around in subtractions. We'll see. But morally, like, if you miss any point, if there are two things that are adjacent, great, we'll find a hit between them. And if you're at one of the boundaries of your measurements, either the very first or the very last, you won't find a match, and that's fine. No result will come out of the join. It's not a problem. So we've got this join. We'll see in a moment whether it's crashy and whether we want to guard this a bit more carefully. That would be a responsible thing to do, but I'm just going to sort of barge ahead for the moment. So what do we have now? We have some records that the join produces. These indexes that we really don't care about anymore, to be totally honest. Like once we've lined things up, we only really care about whether D1 and D2 have a certain property, which is to say, if D1, so we want an increase in depth, so we want D1 to be strictly less than D2, I think. Now this will produce both true and false as results. And then we can do a count on that and inspect. And let's just see if this compiles. Yeah, so Rust will panic in debug mode if you try to subtract incorrectly. So we could do this a few ways. Like one sane way, for example, is just to filter this collection down. It's a bunch of work. I mean, sorry, it's easy to type, right? Let's just so this is now a thing that I probably works a little bit better. Oops. Subtract with overflow, really? Oh, so silly. Sorry about this. That filter needs to be on the inner depths here. So let's actually, we'll make for clarity, a new thingy for this, and this filter wants to be here instead. And now we're going to join with next. Great. So we see a bunch of true statements and a bunch of false statements, and they add up not to 2,000 anymore, but hopefully to 1,999, because that's the number, if you've got 2,000 things, that's the number of interstitial moments, adjacent pairs. Cool. hopefully this is the correct answer. Sort of curious. Let's see. Oh, that's the right answer. Thank goodness. That was very embarrassing. As they get harder, you don't often get the correct answer the first time. No, I said filtering is a lot of work. As you saw, super easy to type. There's a different way to think about this, though, which is it's a lot of work to compare every single index to 0, given that we know that only one of them is going to miss out there. A different thing we could have done instead of subtracting 1 would be to add 1 to everything. We're starting with some background knowledge here that things start at 0. We don't expect to reach the usize max value to the whatever 64 minus 1, that type of thing. So we could have just instead done a plus 1 here instead, and or let's just do it here instead. Plus 1, and then we join with depths. What does this do? So this says take each of our measurements, shift it forward by 1. So 0 is going to turn into a 1 temporarily, and then join with the actual measurements. So we're going to fake out where we are. We're going to shift our copy of depths forward just a little bit, then try to line them up. The first result will still be the first of the two measurements, but we'll basically have said we don't really care about looking for the thing that comes before index 0. Let's see if that works out. It did, and we got the same answer. You can't see that it's the same answer, but hopefully you can go roll the tape and check that was the same answer. So this is something that's a little easier, I suppose, in the sense that we don't do that filter on all of the records to do approximately nothing except remove one of our 2,000 records. But there's lots of solutions for how to do these sorts of things. This has the appealing property, all of them do, I suppose, in this case, but like if you go and you add or remove a single depth measurement, like I'm not sure entirely why you'd get that, but maybe your data are coming in incrementally. You got lots of data, and then the measurements refine themselves, maybe, who knows. The join does a great job of taking one change due to depth and only doing the work proportional to the single individual changes. We could, for example, if it weren't so tedious, load up all of this data in an incremental fashion, one measurement after the next, and we would see these numbers evolve from 2 zeros, 0, 0, all the way up to these correct answers. Maybe we'll get there. Maybe we'll find a problem that really calls on us to do that, but at the moment, it just makes plenty of sense to just load all the data in there, since there isn't really a before-after we need to look at. Let's look at the second half of the puzzle. I haven't seen any of these. Oh, here we are. Yeah, perfect. Because you don't get to see them until you type in the right answer. And I think once you've typed in the right answer, it remembers who you are and that you've done that. All right. So we're going to consider. Okay. So what they're telling us, right, is that lining up these measurements is not actually what we want to do. We're going to look instead at the sums of 3 measurement sliding windows. So what does that mean? So we've got our various thingy-ma-whatsits depth measurements, and instead of comparing sort of 1 by 2 by 3, we're going to take a chunk of 3 of them, slide it forward 1 unit, compare it to the next chunk of 3 things. And I presume count the number of times one of these slides forward represents an increase. So we're now going to try to count the number of times the sum of measurements in the sliding window increases. Da, 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 da. Increases from the previous. Okay, sorry. Yes, previous sum meaning the previous 3, not the previous problem answer. So there's a few ways you could do this. I'm going to try to be clever right out the bat. one thing to observe, I mean, we could go and we could compute 3 wide sliding windows. We could go and compute 50 wide sliding windows. What's actually going on here is so if we look at what I'm not really sure, the A's and the B's, clearly 2 of the numbers are in common, right? So they're irrelevant. All that we're really comparing when we compare A and B's is 1999 and 2010. And we're comparing the B's and the C's, we're only comparing 200 with 200. That's not a change. So in a sense, all we've done, I think, is shifted the window to be, instead of comparing adjacent measurements, we're comparing 3 apart measurements. I think. Let's, again, could be comically wrong. Let's see. So if we run back over here, and we just do a +3. Is that right? 1, 2, 3. Sounds right to me. So we've now got a true rating of 1645. Let's see. Oh, that was right. Okay. So it turns out that sometimes I want to say they're misleading in the puzzles, but sometimes if you sort of scratch your head for a little bit before just going and implementing the thing that they're asking you to do, you went out. And this does have the appealing property. Yeah, if it mattered to you, you could make this number be as big as you like, and it would still be a very simple amount of work that's going on. We're not doing 3 wide windows anywhere. And as the window gets bigger and bigger, clearly, like window size times sequence length, that's a waste of a lot of work when you could have just compared the 2 elements at the boundaries. All right, we're done. Hooray! Let's return back to the advent calendar thing. I don't know what these colored squiggles mean. I think maybe it like draws a picture for you as you go down. Let's continue though. So day number 2. Day number 2, we're in a submarine, if you recall. There's some depths. And the submarine can apparently take some commands: forward, down, and up. Is it just forward, down, and up? Don't go backwards. At least not yet. Forward, down, which increases the depth. So forward, down, up decreases the depth. They even say this, that down and up affect your depth, and you shouldn't think of them as, great, decrementing. So we're going to get presented with forward, down, a sequence of actions someone's going to take. We start at 0, 0, and we end up at some horizontal position and some depth, and multiplying them together versus, I see. This is, I guess, the signature for your answer to make sure that you just have to put in one number. So compute the horizontal position and depth. You'd have to, you would have after following blah, blah, blah. Great. And then you multiply them together to get one number. And here's the sort of beastly horror that we have to deal with. Just copy it. So, oops, I didn't want to copy that. I want to make a day 2 that will open up. How do I get that? All right, here's our horrible input again. We're gonna, word. There has to be a better way of doing this. So what I'm doing, this isn't probably like tabbing in enough that these looking for that tab pattern is uniquely identifying, and I can just scooch to the end and put a comma at the end of things. But I need to do more than that, don't I? I need to. Oh, I could. Okay, let's just leave these as strings. But this, you could totally use this nice editing thing to put together an enum, for example. Actually, let's just do that. That seems less annoying. I mean, you're supposed to take these things in as text, but we could totally build in enum command. Amazing. And what we'll do now is hop back to each of these things that I said we're going to let be strings. They're not going to let them be strings. We're going to make them into it's very possible that I have contaminated the rest of my program too at this point. We'll have to check if I've taken every occurrence of the string up, for example, and replaced it with caps up, but hopefully that will present itself. So we've got some input thing there, and we are going to again want to grab all this input and put it into our collection. Let's again do some stuff, though I'm going to do things a little differently just to explain. Okay, these aren't depths anymore, but so we're going to take our commands, which is input, and we're going to iter through it. So we don't actually want to make a copy of all this data because I should have checked on the previous. Probably still can. We'll get back there. On day one, whether this still works with multiple workers, it's a great thing to check out. Input.iter.enumerate, which is going to produce pairs of usize and command. We're going to filter that based on position and command where position appears equals index. This is now an iterator of okay. Well, we're going to see what Rust thinks about ownership and all these things. We want to get this into a state where we can dump this into our data flow. I'm doing it sort of outside the data flow, and I'm going to see if I can avoid allocating another vector as we go and do this. So if we take our commands and do commands dot to stream and don't do anything else, except maybe let's dot map them with. So we're going to pause on the CMD. We're going to turn this into. I'm not sure if we actually need the position, but let's just keep it for the moment anyhow. Great. So we've turned everything into a differential data flow collection. Let's see if did I not? Where did I save this? Terrible. All right. We absolutely don't want to see all of that. And we'll see if we can run this. Ah! All right. No, we cannot. So what's going on? So we are running on. Well, we're iterating through all this stuff, filtering it down, and .clone is not doing exactly what we want. So let's throw it in over there. Oh, I need to, sorry, some of this is me being, Well, bear with me just a moment while I remember why it is that it's horrible stuff. So we could totally do this, right? Oh, no, we can't totally do that. Why can't we do that? These are a few more minor complaints. These are things like index and peers are being used but not copied. All right, so things are better now, though. I gotta say, not deeply satisfying, right? In the sense that cloning the entire input vector only to filter down things is silly. Let's just try a moment of figuring out if we can fix this. One answer might be, no, I cannot fix this live, but so what are we going to have? We're going to have this is a command that comes through. So let's cannot infer an appropriate lifetime. Blah. What we would like to have happen, and we'll figure this out, or we'll just go back to the terrible version. We'd love to have input be captured by the closure, sort of have ownership moved into it, and then have this thingy, whatever it is, be able to use input as it likes. What we might just be able to do instead, let's see if this works. We've got input out here. We're going to take essentially the same fragment. And instead of building it out there and trying to have an iterator that happens to live, let's just put it all right here. Let's see what happens with that. Method map exists for vec. What line are we looking at here? Line 1000 and whatever the... Yeah, okay, sorry, that's just a matter that we need. Lifetime may not live long enough. Argument requires that tick 1 outlives that... okay, no one wants to see this, so we'll just do this. And we can delete that. Okay, so all that work being done, we now have a bunch of commands in there. And what we need to do, these are all of our commands, we need to just figure out the horizontal position and the depth and the horizontal position reached. And we can do this a few different ways. There's like a slick differential data flow way to do it, and I think I'm just going to try that because I like that. So differential data flow is plenty good at adding things up. Right, that's one of the things that it does is it, all those counts that we saw, for example, has got some records have some data payload, and then you saw plus ones attached to them. It's the same plus ones that live right there. We're going to do a similar thing, knowing full well that we'll have to undo all of this once we see what part 2 is, because we wouldn't possibly be so lucky as to for that to work out. But we can take commands, and there's this nice differential data flow explode thing, which we can take our records of position in a command. I think the position is probably irrelevant. And we get to produce, well, in the explode command, we get to produce some data and a count attached to it. We get to essentially produce these two fields, whatever data we want to use here, and whatever number we want to put in the output. But we don't have to just use a number. This is the smart thing. And I'll show you what I mean by that. So we don't really care about the position, as far as I understand. And we do care about matching the command. So if this is a command, or options forward of x, we're going to produce something. And I'll need to go and check what that something needs to be. I believe it's tuple mods, yeah, so I think we just get to use tuples. So what we're going to do is, instead of just having a number 1 or something like it, we are going to have a two-dimensional diff that is going to contain both the horizontal distance and the depth. So we move forward, for example, horizontal distance moves forward by x. So it's x-axis, y-axis, yeah. And 0, if we have command up of, we're just going to call it y so that no one gets stressed out. 0 and up is going to, since this is supposed to be depth, negative y, command down of y, 0, y. So this should make a new collection. Actually, sorry, we've done a bad job because we need to output not just this nonsense, not just the +1, but also some data. And actually, Explode wants us to produce an iterator over that data. So the iterator can just be something simple like sum, which just says, yeah, I'm an option. I've got either one thing or nothing, and I happen to have one thing. Sort of an easy way to do it. And we'll just put a boring empty tuple key on these things. Basically, we're saying there's no, these accumulations that we're doing, we're not doing them separately for different submarines, potentially. We could totally do that. That could be the submarine ID. But we've just got one submarine that we're doing at the moment, so, right. And we'll just throw this down here on its own line to make things format a little differently. We're going to do a count. Count just says, ooh, take all those pluses and minuses on all of your records, add them all up, and then we can inspect. And we'll see what happens here, and we'll see if this builds. It does not. Oh, good point. So we said these things were going to be U sizes. Let's make them be I sizes. Just we could work harder and do a conversion. Let me also just tidy up some of these warnings. We don't really care about that. All right, and we ran it. And we ran it. What did we get? So horizontal distance. Oh, sorry. Okay, sorry. We did our count. We have to multiply them now. Right. So we have an empty tuple key. And we can just put that in there, and that sort of confirms, Russ will yell at us if that's ever not true. And then we have horiz and depth, and we want to multiply them. All right, that's a number now. Phew. Again, low-level stress each time I put that in. I'm not going to redo this recording. So, part 2. Well, okay, it's actually more complicated. What's going on? So actually what happens is we have this aim thing. So down, okay, so up and down are probably, it looks like, going to change where we point, right? So, these two things do manipulate something. Each time up and down change, something does actually happen. But when forward comes, we scooch forward by x units, and the depth is sort of multiplied by by these things. So this is now going to be much more, unfortunately, much more tedious to solve. This is where a lot of the advent of code stuff often goes, where you go from doing some nice data parallel computation to what I think is going to end up being a fairly sequential bunch of work, which is too bad. So let's see, we might just cheat our way out of this too and do it in a shady quadratic way. This example, so I think we understand what's going on, or I think I do. Hopefully, y'all do as well. Up and down are accumulating some quantity for us, such that each time forward does happen, zoom, we go in some direction. Now, I'm just gonna. I don't think of a great way to do this that doesn't involve some heavier weight stuff, specifically parallel prefix sum, which I had to do a lot last time I did Advent of Code. But I think we can cheat our way out of this a little bit by doing a cross join. So let's talk through what's going on here, which is the only time anything changes about our horizontal position or depth is when we see a forward of x. And when we say forward of x, horizontal position goes forward by x, and depth changes by the ups and downs that have occurred before forward of x. So it's good that we have those positions in hand. And we can be a bit sketch here and just basically take all of the forward statements and their positions and join them against all of the up and down statements and keep any that are at a prior position, and just add up everything, basically. Each time we tick forward, grab all those ups and downs, figure out what they correspond to, multiply by forward of x. This is an interesting trick here, potentially. We might be able to use the join to do the multiplication for us, which is in no way redeeming, but is sort of interesting. So let's, after following these instructions, horizontal, okay, we I think need to do the same thing, and then multiply all the stuff together again. So let's try that out. We've got our commands. In fact, I'm just going to leave this in as part 1 done with too much cleverness. And let's do part 2 now. So as said, let's pop apart the forwards and the ups and downs. And I think I'm going to try to make this a bit smart as we go, so that I don't feel quite as bad about the join that we're going to do. But we're going to let forwards be a thing. What type of thing is it going to be? I'm going to turn it into a collection that is just positions, where the count is the unit stepped forward. So it's going to tell us basically, at each moment in time, at each position in the command sequence, we are going to have potentially 0 steps forward or 5 steps forward, and rather than record that as data, we're just going to put that into the payload. Put that into the diff field. So we're going to do something fairly similar here, because I do want to. It is otherwise fairly annoying to program the differences into these updates without using explodes. If I have a single record that says Frank, 27, I want to actually turn that into a collection that has a record Frank that occurs 27 times. You don't actually want to do anything 27 times, right? You want to be able to write some logic that says make the 27 be the apparent multiplicity. So we're gonna do an explode again to get our forward out, and the way this is gonna work is Up and down mean nothing to us. Only in the case of forward do we care to do a thing. And we are going to use pause, and we are going to produce sum pause comma x. So what this is doing is saying for each position, if it happens that we have found a forward command with forward motion of x, produce as the output that position as a piece of data, and with the multiplicity that is the forward distance traversed. We're going to have another one, aiming, which is going to be very similar, except we're going to do it for ups and downs. So forward means nothing to us, but if we have an up or a down, okay, I'll probably get the sign wrong on these again. Let me just check over here. Up increases, aim. Up decreases your aim. But great, okay, so up is a subtraction there. All right, and now what we're going to go and do is take these two commands, the forward bits of motion and the, sorry, let me actually check to see if they, great, it does check at least, cargo check. Take these two commands and just join all the records together. What do I mean by that? So we do forwards dot map of pause is going to go to empty tuple comma pause, which is to say the pair of a key, which is the empty tuple, and the position at which things have happened there. We're going to join that with aiming dot, same thing, aiming map of pause, empty tuple comma pause. And what do we have now? We've got a bunch of, let's try to write it out, map. Do a map, but actually we want to do a filter as sort of the first thing we want to do. Filter, let me try to write down the type. So this is a tuple that's coming in. The first thing is a empty tuple, that's our key. And the other things that are going on is pause 1 and pause 2, where the first thing is the forward motion, the second thing is the aiming, and we want to keep these if pause 1 greater than pause 2. Right, so we're only interested in the bits of aiming that happen before the forward motion. And then we're going to hit this with a map, and we don't really, the empty tuple beginning we don't really care about. And in fact, actually, what do we care about here, actually? I think I need to do something. I think my have the join multiply things is going to be a little too silly. Or sorry, I think we can do this and we can get the depth out, and we'll have to get the forward position a different way, which should be super easy because it's just adding up all the forwards. But otherwise, we'd have to figure out how to multiply two-dimensional tuples. So we'd have to figure out how to do these things. Is that right, or can I finesse this somehow? I don't know a good way to finesse this. So what I was hoping to have happen would be the counts that are in, because basically what we want to multiply forward motion times the depth thingy to get where does our depth end up. And I was hoping to also stick in there somehow the forward motion ometer as well. But I don't think that's going to happen. So let's, we've kept all of our aiming statements that precede our forward motion. And I think actually we just want to like more or less say no one cares about that data anymore. No one cares about the payloads of these things. We just care what it ends up being. So let's print out. We're going to print this out in two parts because I guess the forward motion has stayed the same, probably, hasn't it? We didn't record what it was though. So to get forward motion, we just take all the forwards, which are again a bunch of positions, and we don't care about those positions anymore. We just want to add everything up. So we just want to say, don't care, you are an empty tuple. Bum-ba-doo. And I think what I'm going to do is actually try to make this something that we can join together to print out the output on one line rather than have to get the calculator out. Feels a bit bad to do that. So both depth and horiz are empty tuple keyed counts of accumulations, I suppose, where we have a depth computed up here by adding up all these aiming things that come before each of the forwards, and then just adding up all the forwards. So we'll join these two together. We will, I mean, they're just single records, so we can just inspect the result, which should be D and an H. Let's see if this compiles. No, it does not. Unclosed delimiter, yeah, that's very believable. All right, so we probably, I think I deleted a thing that I shouldn't have deleted. This inspect was expecting something else. What a mess. Let's try to figure out what it was expecting. So we've just joined these two things together, and it wanted to see this key, then a bunch of weird other things. Why did it want the weird other things? Depth, yeah. Horiz, yeah. I would have thought depth would have type, data type that was, since we just did a count of empty tuples, empty tuple comma I size. Horiz would also have empty tuple comma I size. And when we join them together, these two things, D and H, each would have been an I size. I think it's just a matter of doing this, but maybe we'll get a better error message. Expected tuple. Found unit. Can't multiply. Yeah, okay. I mean, no one wanted you to do that, obviously. So what is the type that it thinks join has here? Well, we can throw some annotations on these things to see. So we think this should be, I think it's I size. Let's use differential data flow. So let's pass the try to throw a type onto this to see what it complains about. So we might have wanted this to be I think that's what join, unless I'm massively confused about what in the world is this. Join, okay, join is supposed to produce, yeah, that's what I thought, but I'm a little confused apparently. Data type, there's a pair, the key, and the two value types. So in particular, I might have thought it would look like that. The key, which is the consequence, and then the two different counts that we got out of things. Got this inspected, so useless. Put this back in here. Expected. Tuple with 3 elements found with 2 expected. 2. So, okay, let's see. It's possible, I wonder, probably what differential data flows inspect does is want to know also the time and the diff of these things. Yeah, okay. So it wants you to tell it what to do, not just with individual records, but actually with all of the differences. Well, here's the thing. I'm a little skeptical if that's the right answer, but let's check. No, that was the right answer. Amazing. All right, so this is unfortunately a terrible way to do this on account of this join here means that we're going to do something that's quadratic in our input, and that's gross. No one ever wants to do quadratic in their input big data stuff. Now, there are better ways to do this that I really don't want to get into right now. There's some supporting code in differential data flows, prefix sum infrastructure, that allows you to do things, and it's basically, like if you think about it, this aiming stuff, it's not totally different at every different position that's out there. It adds up, and if we were smart, we could go through and sort of add things up, and then each time we hit a forward, look at the current total. If we're even smarter, it turns out we could use this prefix sum stuff, which goes and takes all of these moments in aiming that happen and breaks them down using, I don't think it was hardwired in or what, but essentially saying, for each power of 2, let's slice up the space into the various powers of 2s, add things up in those powers of 2s, and do only a logarithmic amount of work. So instead of a quadratic amount of work to figure out what a thing should be, we do a logarithmic amount of work. Sorry, linear times logarithmic amount of work instead of quadratic. I wrote all of this stuff for the last time we had advent of code, because there, again, there's a lot of stuff that looks like there's actually a sequential state machine that you're walking through, and that's definitely a stressful thing for data parallel, big data compute stuff. Just a little casually at the prefix sum stuff. You can read all about it in prefix sum, though unfortunately actually you can't read too much of it because there aren't so many comments. If there were more, I'd be able to figure this out probably a little bit faster. So there's a trait prefix sum, and it's defined on collections whose data type are essentially a position and then some value k. And where I guess, I'm not sure why k, but I think k is the sort of the data payload. And then we, oh, sorry, it's more complicated than that, isn't it? It's a collection whose records are a pair, I see, a pair of a position and a key, and then something you're adding up. So this does make more sense. This is a key. And a thing you're adding up. which for us is this aiming thing, right? We're adding that up as we go. There isn't a key of interest because we're just doing this for one thing, and the U size would be the position that we got sort of in the command sequence. And what we can do, it looks like, I'm sort of just getting my head around this again, sorry, because this is, we're not going to barge through these problems as quickly as you might have imagined. There are two things, there's prefix sum and prefix sum at. So prefix sum is going to take a whole bunch of these, let's just restrict our attention to aiming at the moment. Right? Aiming says, I am a bunch of moments in our command sequence where I change a contribution to this thing that we're accumulating, our aim. And prefix sum says, if you give me that pile of input data, if you give me a 0, just 0, turns out, in this case, and some function that's good at combining these things, I can produce the same type again, so a collection where the data are an integer, a key, and a thing that we're adding up, where I believe, once we go on, is that it's the accumulated value, not the original diff. And it's going to do this not doing a quadratic amount of work, but just doing n log n. Right, so we could have done that join and said add everything up for, and we'd feel sort of gross. But this lets you do it with a logarithmic amount of work. It's pretty handy. And there's some other stuff that you can, as a sort of a smarter version, that allows you to go into just a few of the locations. Don't compute this for everything. Don't do n log n for everything. Do sort of the order n. You can do some aggregations and then do logarithmic probes at the locations you're interested in, which would be interesting, for example, if you do a lot of aiming and then occasionally do a forward. You might not want to do as much work, and you could be smarter. Though we could probably just do the prefix sum. I'm sort of curious to try this out now. Do the prefix sum on the set of things that are forwards, ups, and downs. Forward doesn't happen to change anything, which will allow us to then just do a join with the forwards and read out what is the accumulated value at that moment. Yeah. And then we'd only have done n log n total work instead of quadratic amount of work. It also has the potential to not dramatically, kind of cost a lot of work when you go and you apply a small diff somewhere. If you put another forward in, for example, incrementally, you'll get an efficient change out the other end, whereas you wouldn't if you did things with sort of quadratic update approach. I'm going to try this, actually. I'm sort of curious to see, because it doesn't seem so bad, like famous last words, but... So we'll want to bring in, where does this live? Algorithms, prefix sum. So I want to bring in, we're just going to do this a different way, which is I guess I have to lift a bunch of these things into data rather than the diff themselves. That'll be fine. We can still use the same forwards if we want. So let's try this. We do part 2b. We're going to do use differential data flow, algorithms, prefix sum, just all caps prefix sum, prefix sum. And what we're going to do is we're going to make a new collection here of our commands. And I don't think we're not even going to explode them. We're just going to just do a little mapping on them. So pause, comma, cmd. Now, position is important to keep around because we need that U size. And what we need to figure out from the command is what is the contribution to the accumulated aim basically at this point in time. So we're going to do, again, we're going to do a little match here on the command, and if it is, sorry, I need to copy and paste just to get this, but so up is a negative x, down is a positive x. That's the change, and we're going to want to produce as our output now. I believe what we needed was a pair of a u size and a key. Where are we? A pair of a u size and a key, and then the d. So the pair of the u size is going to be the pause paired with a nothing, and then we're going to want the change. And that's what we want to produce as our map. And then I think maybe just prefix sum, where we give it a 0, which will be 0, and a combiner, which is just a closure that's just going to add these together. And that gives us now all of the accumulated measurements at each of these locations, including the forward locations. That's sort of important. Double check with this. So this still has our keys present in it, so maybe we'll want to delete. Sorry, it has the key, like this silly thing here. So we're gonna pose. Sorry, the problem is that forwards does not have that key, so we can't just join them yet. But let's do we're gonna just screw around with forwards anyhow, because it also doesn't have a payload at the moment. So let's just join this with forwards.map. So forwards has a position in it, so we're going to want to make that be a pause, comma, nothing. But not just a pause, comma, nothing. Sorry, all of these parens are super annoying. Not just a pause, comma, nothing as the key, but a pause, comma, nothing with a nothing value attached to it as well, so that we can perform a join. Join really wants you to have a value attached to your keys. This is the key right here, or sorry, with this paren. This is the key. It really wants to have a value attached to it. We don't need a value, so we just join, and that will now give us a bunch of positions where we have read out. So we will have a pair where the first thing is our position that I think we don't care about, like from this point going forward. We will have now two things. We're going to have the aim that we aimed at, and a nothing. And I think we actually want to do, again, one of these explodey things here, because we want to take that aim and we want to put into a sum of nothing, comma, aim. Is this right? Oh, okay. So what we're saying is, for each of these forwards moments, we know that all of our prefix sums has a report for each of the forwards. We really just care to find at those forward moments, which is this specific pause and a nothing key. Show me the aim at that point and make that aim be the amount of change that we experience, where fortunately the join is going to go and say, if you got 57 copies of forward in there because you went forward 57 units, we'll correctly do the multiplication here for you. And each of those 57 will turn into an additional bit of aim. So what I'm going to do here is print out the D and the H separately so that we can actually see without trying to redo all this work and what we have. On account on there, this is just meant to be the depth. So let's just print this out. And see if it runs. May not. Closing delimiter screwed up. It's very believable. Good expression found. So did I screw that up? Prefix Sum. Oh, sorry. That shouldn't be there. So it looks like there's an explode maybe with an unclosed delimiter. What a nightmare reading all this stuff. These all match here. Some. Oh yeah. Well, no, I take that back. 1, 2, 3. 1, 2. Jeez. Yeah. Okay. Just needed to close the after the curly braces. Put a closing thing around it. It's good. A lot longer to build because unfortunately Prefix Sum has like a bunch of interesting code in it with iteration and stuff like that. All right, and we did actually get the same depth there. So despite this being potentially a lot more complicated in terms of the data flow and stuff, should have been more efficient asymptotically in the amount of time it takes us to accumulate all this stuff up. And we would have gotten the right answer, as far as I can tell. Like if we took this as our depth, we wouldn't have done this horrible cross join up here. That is potentially really inefficient if you have a very long sequence of subcommands, which of course we don't. Great. Okay, so that was day 2. Let's. Is that the picture that it's starting? I can't really tell what's going on. Let's look at day 3. At some point, I'm gonna need to take a break, but it's actually not so bad so far. So it'd be interesting to see how painful these things are. All right, day 3. Binary diagnosis, list of binary numbers, which when decoded can tell you some things. All right, take the binary numbers, generate new binary numbers, two binary numbers, multiplying these two numbers together. So we figure out each bit by finding the most common bit in the corresponding position of all numbers. So we sort of we take these horizontal binary numbers and we look vertically, I suppose, and figure out which one is most common. Just do a count basically, and then reassemble the number, I suppose. So the most common one, that gets us the gamma rate, and the least common one, so I should just flip all the bits. So you definitely won't do this a second time, we'll just do this once and then flip all the bits. And yeah. And then you multiply things together. All right. Well, this seems easy enough for part 1. Let's try this out. So, zoop-a-doo, source bin, day, copy day 1 because it's not a disaster. Source bin, day 02, 03, $. Day 03, 3. And of course we're going to want to delete this massive pile of filth up there. Let's get our puzzle input. Great, massive pile of stuff. And I'm going to put them as strings. Why am I putting them as strings? I don't know how to put them as binary. That's the main problem. You can put them as strings though, and we'll iterate through them as characters and sort of decode them as they go. I have a plan already for how to do this, but All right. Unfortunately, I have to. It winds me up that the comments are no longer about depths and stuff like that. We could have stolen day 2's ingestion trick. Let's try this, just so we feel less bad. Oh, I cloned the whole thing anyhow. Never mind. It's terrible. So I don't think we're going to care about the position too much here. I guess we can keep it around, I suppose. But I bet we're not going to care about it for the first part anyhow. So this dumps a whole bunch of numbers in here. This is, figure out the most frequent thing is clearly like not order dependent yet. So we've got a bunch of numbers. They're partitioned up nicely. I still didn't check whether this is the right answer. Still with number of workers, but number of workers varying. But oh well. So what we're going to do is we're going to turn our collection of numbers into a bunch of pairs of character and then position in the sequence. So or we could use bools, I suppose. And then we're just going to do a count. And do a count, and then we'll do a reduce, basically asking for each position which of the two counts are more interesting. We could do even less than that if we wanted, because we happen to know that the results are binary, so there's only like one count really that matters. There aren't really two counts. But let's start typing and see what happens. Alrighty. Does this actually build? I forget. Oh jeez, I just overwrite this poor thing. Okay. Yeah, how happy Rust is having just strings presented at it without. No, okay. Wait, hold on. There we are. Yeah, maybe this is fine. So we take all of our numbers. They're each currently some string E thing. Actually, I have no idea what type they are. Hopefully string, but possibly strref or something like that. In which case we'll fix it. And we're going to do numbers dot map of, and it turns out we don't really care about this at the moment, about this position thing. We do care about the string thing though, and we're going to want to iterate through it, which is probably the character iterator. Does that sound right? So if we do, should we do a flat map? Because we want to take each string and produce multiple output records. So we do string. We need to, flatmap wants us to produce an iterator as output, so we'll do that. So tempted to do this in a screwy way again. Okay, we're gonna do it. Since we're producing iterator anyhow. So string dot cars, I think, dot enumerate dot map. And what I think we've done here is we've asked the string to tell us about the characters in it. That's now an iterator over characters. We also want the position in the sequence. Hopefully all of our binary numbers, they've put explicit zeros at the front. Okay, so we don't have to worry about that horror. And what I expect that this is equal to now is a position in the string itself, not this position up here in the input, and then a character, C, I suppose. And what we're going to do is turn this into a because we're adding up two things, number of times zeros occur and number of times ones occur, we can just use a boring key of nothing. And then the thing basically says if this is a 1, let me do this a different way. We're going to learn that I know approximately nothing about string processing in Rust. That's fine. Whatever we want to do here, if we see a malformed input, we could just produce nothing in our output if we want. It's possibly the safest thing. So we're going to explode this, meaning take each of these strings and turn it, disaggregate it essentially into a bunch of individual boring records. Now this is wrong because we don't want to say nothing about where it is. We want to track the position. So we're producing a tuple whose data payload is the string position, so 7th character or 6th character or whatever. And then it's going to have attached to it 2 different counts of numbers. The number of times we see a 1 and the number of times we see a 0. It might make more sense in this order. And then we'll be able to look at those counts and say, ooh, the number, 0 is in the majority or 1's in the majority, that sort of thing. So to do that, we would do a count afterwards, which is going to say for each position, max, min, whatever. And we could just report these if we wanted to at the moment, though we're supposed to go and produce these two numbers, which we can do in a few different ways. What's a good way to do this? So we've done this count, which is going to tell us for each position the contribution to the thingy, and we want to make sure I understand this correctly. We want to produce these 2 different numbers, essentially the most frequent and least frequent number. So. And it's not hard to do. Why is this? We can just lump all this data together and say. So someone has sorry. At the end of the count thing, we have a string position and a 0s and a 1s, which I'm naming. We're not going to use these. So we're just going to lump all this stuff together. Should we or should we? We could figure out most frequent. This is not hard computer science that's coming up. I'm just trying to figure out the least offensive way to go and do this. Let me just snag this here. Just gonna let the counts be this thing. And we've got two things, delta, gamma, and epsilon. Is that right? So gamma is the most frequent one. So we're gonna take the counts. We're gonna map them. So what are we gonna do? We're gonna look through and we're gonna try to figure out, in essence, which contribution should we have in each of the positions? Actually, one way to go and do that is just with a filter, right? Because a 0 contribution, just ignore. We don't add anything up. So we are going to go and zeros and ones, and we're going to keep, so with the most frequent thing, if ones is bigger than zeros, then we keep it. And I have no idea what happens if they're tied. Hopefully they're not tied. So what's going on here? Sorry, we're running through. We're looking for to figure out the most, the number, binary number that is the accumulation of all these things. We're looking for those positions that have a 1 in them. And that's those where the 1's count is bigger than the 0's count, and we're going to want to take that and say, great. In such a case, take this pause and so annoying. This is another case where you want the or the explode thing is beneficial. I feel like that should maybe be the only programming primitive in all of differential data flow at this point. So we'll do another explodey thing here. Again, this is just another case where since we want to add things up, but the thing that we want to add up occurs in the data part of the payload. So anytime one of these things, we're going to do a record that has a key of nothing in particular. We could make it be like the string gamma or something like that. And actually that could be sort of fun. No, let's do that. So in fact we're not going to filter these things. We're literally going to take every position there's either going to contribute to gamma or epsilon. So we'll just literally take each of these things, z's and o's. Let's just rewrite this from scratch. Bunch of z's, bunch of o's, and we're going to say if O is greater than z's, then we're going to produce sum. So we're always going to produce a record, so we should always produce sum. So if the 1s are greater than z's, this contribution is going to go towards gamma, otherwise it's going to go towards epsilon. We're just going to let this be the thing we produce in the output. So we're going to do sum of is gamma, comma, 1 shifted by pause. So what is this doing? This is basically saying for each of the positions that we're seeing in our string, that's going to contribute a 2 to that position to either to epsilon or to gamma. We just need to figure out which one it is. It contributes to gamma when the 1s are bigger than the 0s, and contributes to epsilon when 0s are bigger than 1s, because the epsilon's going to flip the bits. And now we do count and then inspect. And then we debug for a little while. Close delimiters, so string chars enum map. Is this yeah, this is not closed appropriately. Enum map, great. We definitely forgot to put a little pipe there. And we're supposed to multiply these in together, aren't we? Well, why don't we find a way to do that? I guess we can just do a reduce on these things and add them. What do we want to do here? So since we're just multiplying them together, we don't really care about the false versus true, so we're just going to turn everything into a we're going to take, don't care about your false or true witness. We're going to take your total, turn that into empty key total, and then do a reduce. The reduce, just you give it a closure which says what's the key, don't care about the key, input, output. And we need to read through the input and produce some output. Our input, what we expect to see is, actually, I can probably just print it out if we want to. This is not how you should write differential data flow code with side effecting things in your closures other than inspect, but still do that. Then we'll want to do output.push, where we're going to push in one copy of a record that is input 0.0 times input of 1.0. Let's see if that works. So that's a candidate. Let's see what happens if we type that in. Oh, it's not the right answer. It's too high. Oh no. All right. So we need to try a little harder apparently. This is good because we actually get to do some debugging, which the previous things I guess worked. But anyhow. So another thing that we can do is turn to day 3 is take the example input and make sure that we're getting the right thing on it. So let's go and see. Great. So we've got some example input, and we've got, I think, some hypothetical example output. And let's see what this produces. So it says gamma would be 13. Damn suspicious. Oh, we're going from most significant digit to least significant digit rather than the other way around. So our binary contributions are all screwed up. So let's see. All right, so our string positions here, like 0 for the first thing that we read, but of course, of course, I don't know. This is meant to represent 22 in decimal rather than, what would this be, 13? Is that right? 13 is what we're seeing over here. So we might be getting the right thing just in this, like the wrong order. So if we've got a string, we've got a string len function. And if we do like the minus pause, this is going to be a little awkward because these are unsigned things. We're not really supposed to subtract them, but we totally can. We need to capture some things. All right. Part 1 is actually that instead. Oh, sorry. This is still. So we're just checking our input, which isn't right yet. Hold on. Looks like we're off by Yeah, factor of 2, which probably makes some sense because we want a 0 contribution. Sorry, is this right? Yeah, we want a 0 contribution. All right, 198, which I thought I saw before. Yeah, 198. So let's get rid of this test input. Let's try this one instead. Hooray! It's the right answer. Great. Let's see how hard part 2 is and then whether we should maybe take a little break. Whoa. Okay, so we're going to multiply 2 more things together. Oxygen, CO2 stuff. Similar process that requires filtering out values until only 1 remains. Full list of binary numbers and consider just the first bit of those numbers. Then we're going to keep only the numbers selected by the bit criteria for the type of rating value for which. Okay, so we're going to look at, I guess, at the first bit and keep some subset of things and throw away some other subset of things. Great. And we're just going to repeat until we're done. So let's see. So we are going to determine the most common value in the inherent position, keep only numbers with the most common value, and the least common value, keep only numbers with the least common value, with some tie-breaking stuff where 1 is more common, I guess, than 0. Yeah, okay. Well, let's see. So this isn't too hard to do if we're willing to just, if we're willing to know how wide our numbers are, right? Like our numbers here are this wide. If we happen to know this length, you can just bake that into bake that into the definition of your computation. I wonder if there's a smarter way though where we. So I'm just going to scratch my head for a little bit and try to figure out. I can imagine we were just given actual real numbers that are all over the place, and we weren't essentially told ahead of time how long each of them were. How would we want to approach this? So if these are potentially unboundedly large or like 64-bit numbers, let's just say, then you start with the first bit and you quickly establish, oh look, everyone has the same bit. Great. Most common, least common, those are the same. Keep going. And you would sort of repeat that process until the first moment at which there were differences in those bits. And that's where things start to get interesting. At that point, there's this divergence that happens between the two processes that where we want to keep one subset. Well, at that first moment, at least, we want to keep one subset for these things and a different subset for other folks, and then they get narrowed down even further to go. So we could just sort of grossly. I'm trying to think if there's a good way to do this that isn't just, again, cross joins. Right, like if we want to do it all in data flow, we don't get to see the answer to what is the most common bit before we start building the next data flow, which is a bit annoying because it means we need to figure out how to determine that information in data flow and communicate it back to everyone, also in data flow, without just getting all the information into one place. And typically, the way you do this is something like a broadcast. Right? You learn what that bit is, and then broadcast it out efficiently to a whole bunch of other folks. It's just sort of a pain to write that as a join or something like that. So I wonder, I'm trying to think if there's a handy way that we could go about doing this. So a different take, right? Make sure I'm not screwing this up. Is that we actually really don't care about all of the we don't care about most of the complexity of all of these things at one time. What we really want to do, I think, as we're building up like a prefix for these bits of data where, so like for the first bit, we're trying to look at zeros and ones, so we just care about that first bit. When we go to the second bit, the only relevant piece of information for us is the first 2 bits, right? This rest of this stuff we don't really care about. We can just sort of throw that away. And what we're interested in counting up are the number of folks that match on the prefix and then the count of what remains. And that feels sort of not so bad because you have the potential to do a bunch of data reduction. So the first thing you would do when we're looking at that second bit is say, great, reduce all this down. Reduce it down to just 0, 1, 0, 0, maybe 1, 1, and 1, 0 if we haven't figured out how to delete that from our data set yet. But morally, just go and look at the first few bits, and then that broadcasting of stuff out isn't nearly so awkward and expensive. And as we climb down, we're only interested in one more bit at a time, and it kind of feels like we should be able to take these collections, this is the thing I'm not sure about, take these collections and ditch, as we learn a new bit, we're going to ditch a little more than half or a little less than half of the data based on the next bit that you see and repeat the process. Now, I'm trying to think of a good way to do that part efficiently. So the goal here, like the trick, right, is like, can we look at as little data as possible for each of the decisions that we need to go and make? And I'm not sure how to do this off the top of my head. I'm going to think about it a little bit. It seems like a good time for a break anyhow. I'm going to think about it for a bit. Y'all are welcome, obviously, to think about it as well. And hopefully come back and come up with something that's slightly clever that manages to only keep its eye on the parts of the strings that it needs so far, which seems easy at the beginning, but as we get sort of wider and wider, there's more to look at, though at the same time we are sorry, I'm going to take a break, but let me sketch an algorithm beforehand, which is we're going to barge through this string looking at increasingly long prefixes of it. The first thing we're going to do each time is throw everything not in that prefix, so like take all this data, just get rid of it, and count up everything over here. And that's enough information for us to know about the next digit that's coming up, the number of people who have zeros versus ones that match each of various prefixes. All right, having done each of those things, in fact, we could just do all those ahead of time if we wanted to. All right, for each of the prefixes, count them up. And then we're going to take that information, that's just a linear, like a n log n total amount of compute that goes on that sort of consolidates down to about, hopefully, approximately linear amount of information because of all of the zeros and ones just end up as one count. Well, then we're going to take that information and we're going to sniff our way through that, essentially. So we're going to start creeping through really nicely aggregated small sets of data So just zeros and ones and maybe 3-letter thing, you know, sort of going along as we do. But before we barge into that, we're going to do a join with our current prefix that we're building up. So we're repeatedly going to take our partial sums and say, before we start doing any judging of the next bits, do a join to get into the right subset of that information. Which is, you know, as opposed to trying to do a join against like all of the linear amount of data, which is going to look like some sort of horrible cross join. We'll just maybe that's not even that terrible itself. Anyhow, taking a break for a little bit, and we'll be back in the future with a hopefully working solution to this. Cheers.